Yesterday we were dealing with the chemistry involving alkenes. Today we're dealing with the chemistry involving alcohols, which remember is a whole class of organic molecules, anything with that OH on the end, and that's the first thing that we see here. So the general form for an alcohol is something that contains an OH group, where there would normally be hydrogen attached to the carbon. So it's a functional group just with OH attached in place of the hydrogen. There are three classes of alcohols, and it's based on the number of carbon atoms attached to the same carbon that the OH or the hydroxyl group is attached to. So if there's just one carbon attached to the carbon that has the OH on it, we call that primary. If there are two carbons attached to the carbon that contains the OH, we call it secondary. And the biggest that we can get is tertiary, where three carbons are attached to the carbon that contains the OH group. Now, each of those mean directly attached. So it's not a big long chain and I count all of those up. It's just looking at that one carbon and how many carbons are directly attached to it, which is why we can only go to tertiary, because we know that carbon can only contain 4 bonds. Its octet's not going to change, so it can't get more bonds than that. It can only have 4 bonds. One of the bonds is already attached to this OH, or the oxygen of the hydroxyl group, and that means that the maximum amount of extra bonds it can have are 3. And with primary, it means that there's 1 carbon, 1 hydroxyl group, and 2 hydrogens. With secondary, it's 2 carbons, 1 hydrogen, and the tertiary means that there's no extra hydrogens attached to that 1 carbon that we're looking at, the carbon in question. Now, here's a way to visualize it. Again, we have this carbon in the center that's attached to the OH. That's the carbon that we're worried about. How many other carbons is it attached to? Well, in this one, it's attached directly to 1 more. The other 2 are hydrogen, so this is primary. This carbon is attached to 2 other carbons. It is secondary. This carbon is directly attached to 3 other carbons, and it is tertiary. Now, we know alcohols can undergo combustion reactions. They're highly flammable. And we know from last year that combustion reactions involve some sort of carbon-containing compound reacting with oxygen, which we find readily in the air, and they form carbon dioxide and water, assuming it's a complete combustion. So the general form, this makes our balancing a little bit easier if you're forgetting the balancing from last year. Generally, balancing alcohol combustion reactions is pretty straightforward, but if you prefer to have something to memorize, you could go ahead and memorize this. So CnH2n plus 1, where N stands for the number of carbons that you have. So if I had methanol, I'd have 3 carbons here, or 1 carbon here, 1 carbon, 3 hydrogens, 2 times 1 plus 1. That would be 3 plus the OH. So that would be my 4 bonds, carbon bonded to 3 hydrogens and the hydroxyl group. But let's look at a different one. Let's try to balance it for ethanol. So ethanol, we know eth comes from 2 carbons, so C2H3OH. Reacting with O2, sorry I don't have a slide for it, forming CO2 and H2O, and that's something that you can go ahead and balance in your own time, just as a reminder. Then we have primary alcohols, and we're going to talk about a second type of reaction that they undergo. So we're done with the combustion. That was the easiest one. But primary alcohols can be oxidized. So they are readily oxidized by warming it with acidified solution of potassium dichromate, and that's a Roman numeral 6. Now we have to think about what is dichromate. That's one of the polyatomics you learned before starting the class last year, and that's Cr2O72 negative, and we've got that right here. Well, dichromate is an orange color, and that comes specifically from the chromium part of the dichromate. Chromium, with a specific oxidation number, is orange. Now, the oxidation number is actually given to us here. That's what this Roman numeral 6 means. And we can think about our oxidation rules from last year when we were doing redox reactions. We know that oxygen is almost always a -2 oxidation number, except when it's bonded to fluorine. So from the oxygen, there's 7 of them. That gives me a total negative charge of 14. Overall, my charge is a negative 2. That means these 2 chromiums have to account for a positive 6 value. Or each one counts for a positive 6 or a positive 12 for the 2 to be that negative 2 charge overall. And we see that the process goes from that orange to a green when we reduce the oxidation state from a 6 down to a 3 plus. We reduce it by gaining electrons. It had to gain 3 electrons to become this 3 positive charge. And that color now is green, which gives us a nice color to tell that a reaction has occurred. Gotta love color changes. This is also the reaction that is in many breathalyzers. It has that potassium dichromate, so when you blow into it, oxidation reaction occurs and it goes from an orange to a green. So you have a nice, easy way to tell if somebody had been drinking alcohol. And the second part, we know that it becomes oxidized, and the reason that it becomes oxidized is because there's 2 hydrogens on this atom or on this carbon atom that can be easily oxidized. So here's a general form of an alcohol or primary alcohol where this carbon is near the end. It has 2 hydrogens. This R stands for some carbon containing compound or some carbon containing stuff that goes off to the side. Maybe it's just a CH3. Maybe it's a CH2, CH2, CH3. It could be any number of things, and an OH. Now these 2 hydrogens that are on the oxygen of the hydroxyl group and the hydrogen of the carbon group are what are going to go away. That's what's getting oxidized. They're losing those. And that means that my carbon now is down a bond. So it has an extra electron, but it's missing one. So it has its original one. It's missing the one from the hydrogen. So this is unstable. And this oxygen is unstable because it's lost the one from the hydrogen as well. So carbon we know needs to have 4 bonds. So the only way that can happen is for it to share its one leftover electron with the 1 extra electron from the oxygen. And we get a double bond. And since it's at the end of the compound, it's an aldehyde. So that first step of the process, that oxidation process, as it loses those 2 hydrogens, is the formation of an aldehyde, which again, remember the general form is RCHO. The second step, if it continues, so if we continue on this process, and you're going to see when you read the text what conditions have to be met for the oxidation to continue, it will keep that R group off onto the side, and it will keep the double bonded oxygen, but it's going to replace its last hydrogen with a hydroxyl group, and so it becomes a carboxylic acid. So we can see here another diagram from the internet, this one specifically of ethanol, losing its 2 hydrogens, double bonding the oxygen and the carbon to form ethanal, the aldehyde. And then we add more oxygen in the form of a hydroxyl group by removing this hydrogen to become ethanoic acid. The secondary alcohols, so the ones that have 2 carbons bonded to it, which looks kind of like this, where these are some carbon groups off onto either side, are more difficult to oxidize. We can still oxidize them, but not as easily. And when we do, we can no longer form an aldehyde because that hydrogen is not on the carbon that we had, or we don't have 2 hydrogens on the carbon the way we did before. We've got carbons on either side. So it loses these 2 hydrogens. This is just it's standing for oxidation state. So we're losing those 2 hydrogens, and we get that double bonded oxygen between 2 carbons. That's a ketone, and that makes it propanone, from propan-2-ol to propanone. The reason there's no 2 here is because that's the only way this one can be a ketone. If there were more carbons on either side, I would need some way of representing that which carbon it is on. It can't be oxidized anymore because this carbon doesn't have any more hydrogens bonded to it that could be removed. So it stops here. There's only this one step. It can only become a ketone, can't become anything else. And then tertiary alcohols, those are not easily oxidized, and so we don't have to worry about them unless we start doing other chemistry with them to get them into something else before we turn them into or try to oxidize them.